Hello, I'm starting the stream at the slightly later time of 4 o'clock on a Sunday, at time of recording, the time of being live, whatever this is. We're going to find out if that's worked or not. Possibly I've decimated what viewership I had, and we're going to build up from zero again. But on that note, welcome to I Have a Star 144 and the Carla Cone, who both followed me while I wasn't live several days ago. I Have a Star, or possibly Java Star, or possibly Half a Star 144. I like it when people have got a number in their username. I can pronounce numbers. Unless it's supposed to be, oh no, I've realised I can't pronounce numbers. Famously, maths 2222222 is really hard to pronounce despite all of those simple numbers. Hello Mary, how you doing? Good to see you. Welcome to the 4 o'clock fun, as we're now calling it. We're renaming? No, we're not going to rename. We're going to keep it as Chill Maths. Coming up later in the day, and thus even more chill. That's how we'll sell it. Right, good. Same plan though. I would like to understand quadratic forms. I'd like to understand, well, ultimately things about prime numbers, and it looks like I need to understand class number to get there. Ooh, that's interesting observation. My phone can still give me notifications even when it's on. Let's press all of the do not disturb buttons. There we go. Very much do not disturb. Right, okay. Last time on Chill Maths, we had this fact about class number, or this definition of class number. We're looking for proper equivalence classes of primitive forms. Now, I'm going to make sure I remember what those are by scrolling backwards until I find them. I know they're important because I've underlined them from last time, so I'm going to have a look back and see what those are. Great. During the week, we had Ailian on the Oxford Online Maths Club again, which is always fun. Learning about magic squares. They told me a fact about magic squares after the stream that distracted me I spent a big chunk of Friday just thinking about this magic square thing rather than doing any work. Always fun, isn't it? When someone tells you something that you're just like, right, I should think about that instead. Right. Restrict attention to primitive forms. Primitive forms, perhaps the ones where there's no... primitive forms are ones where there's no common factor between a, b and c, the coefficients in ax squared plus xy plus cy squared. And properly equivalent seems to mean no reflections. Equivalent under orientation preserving transformations, and I've said I think they're the ones where AD minus BC might be 1 in the Mobius map view of the world, question mark. Not sure. Might need to think about that at some point. Right, okay. Over here, what am I doing? So that was definition of properly equivalent, which I suppose would give us proper equivalence classes under that equivalence relation. And possibly there's some splitting into at most 2 of these cases. And then this paragraph looks like it might be describing some facts about what it means to be primitive, the forms that are not proper multiples of other forms. Primitive. So primitive in a kind of prime sense, I suppose, rather than a primitive as in basic, although those are kind of similar ideas, aren't they? Etymology is not always helpful, knowing where the words come from. It's not always helpful. It's sometimes a trap, and sometimes it just tells you that something is named after Euler. But when you hear something, an Eulerian path, and you think this will help me remember, no, it just means a path that Euler thought about. That's loads of things. Could be anything. Euler thought about many, many things. Sometimes, though, etymology is helpful to think about why is it called that. Why have they decided to shorten this maths definition to a single word like that? Sometimes there's a kind of reason that makes sense to me, and I use that to remember. That's the plan anyway. Right, okay. If all numbers at the top graph are divisible by d, then in particular these ones, the values there, there, and there, are divisible by d, so we're good. We've got this kind of this way of accessing the coefficients, I suppose, which we've used before when we're interested in finding numbers around a point. Oh, hello, Math 222. 22. Good to see you. What are we doing? We've got back to the page that we started on. Hello. The traditional notation for the class number of discriminant delta. Discriminant, I should remember, is b squared minus 4ac, of which there are only finitely many. There are only finitely many quadratic forms of any given discriminant. Looking over there for some reason. Over there is where I store my facts about the discriminant. Good. Okay, mirror symmetries can be detected in the separator line. Okay, we like this because there's a continued fraction fact that we're going to get down to. That's an egg fact, I think, over there. I should maybe do a special stream on eggs again or something. You gotta think about eggs. Maths 2222222. Did you think about eggs at all in between streams? I did not think about eggs. I was going to, but then I didn't. I got distracted by thinking about magic squares. Yeah, that really looks like the chat message of someone who has been thinking about eggs. I haven't thought about it. So if you want to talk about it, you will find that infuriatingly I am just as stupid about it as I was last week. I have progressed now. You know, like time dilation, where you go on a journey and you come back and time has passed at different rates for different people. This is Einstein's theory of relativity. So sort of, if you go close to the speed of light, then you can start to notice that time is passing at a different rate for you as it is for everyone else. When it's like that with the stream, I don't always think about the maths problems in between streams. So maybe I'm the time traveller then. You've gone off and developed whole civilizations, and I've stayed relatively still. I think it's that way around. I think you can go to the future. Yeah, probably that way around. With great effort, you can preserve yourself. Thought about eggs. Did some real eggs. Read all the stuff about eggs on Discord, and then tried to do HU3. That sounds like a good getting to grips with the problem, doesn't it? The sort of things that we talk about around here. Like, have a go at it. See if you can do stuff to do with it. I'm proud of that approach. Good. That is what I would tell someone. If they were trying to write a personal statement on that problem, I would not say try and solve it. I would say try and understand the question and read the thing, try it out, write some code if you can. Skills, not results. Ooh, okay, I'm going to write that down. Pleased with myself there. Maybe I should do more of these at 4 o'clock. Better ideas. It is not known. As far as I know, almost nothing is known. But again, refer back to the stupidity fact. We have some cases where we know it's impossible by, I think, parity, like you say. And we have, I think, a small finite number of examples where we can actually do it, like 6 choose 3. This is moving 3 eggs through an egg box of length 6, going through all the positions, only moving 1 egg at a time, 1 space. I think we've done 6 choose 3. I think we've done 8 choose 3. I'm not sure we've done 8 choose 5 by swapping the eggs for air gaps and vice versa. I'm not sure we've done 10 choose anything. I'm not sure we've done ones. Oh, you think an infinite number of 9? Oh yeah, possibly Super Snowman claimed an infinite number of cases at some point. Right, that's it. Somebody claims to be able to do 2 and choose 3. Oh yeah, maybe that's as far as we got then. Someone claims to be able to do 2 and choose 3. I don't understand it, or didn't spend enough time thinking about it. I personally can't do 2 and choose 3, but you're right, if we add together, I think Super Snowman, or possibly someone else on the Discord, knows about 2 and choose 3. Right. Okay, so maybe that's what we've got to do next, is try and do HU3, try and understand Super Snowman's solution for 2 and choose 3. And then the ultimate choose 3 are impossible by parity, I think. Good, right, okay. It leaves lots of cases, like 10 choose 5, but I think 10 choose 5, yeah, vaguely rings a bell that 10 choose 5 might be the smallest case that we think it should be possible but haven't been able to do it. Or think it should, in the sense that it's not obviously impossible by parity arguments. I think that might be the state of the eggs problem. I should probably write that down because I'm going to forget it. Oh well. And I should probably read Super Snowman's 2 and choose 3 solution. Sorry, Super Snowman, if you're watching. I haven't read your post. Right. Okay. Oh yeah, we've got to do the t-shirts too. I have a to-do list. The design that I made was not high def enough, so my block is that I need to work out how to make my image file better, so that it's like a good quality t-shirt. That's priority numero uno, isn't it? Well, out of all of the many things that I should be doing. Right, okay. Part of Chill Maths is me kind of like remembering, oh, I've made loads of promises. There's loads of work. After this I've got to go and mark student work for tomorrow because I'm behind on marking as well. We got a whole day of tutorials tomorrow to revise calculus stuff together. And they've sent me, I asked for this, but they've sent me so many questions. I sent them loads of past paper questions to do, and then they've actually done them, so now I have to mark them. Ooh, let's put it on the list. Let's see. Does Spreadshirt even do dresses? They do some things. They do some things. Yeah, that's more of a hoodie. Okay, possibly. Okay, we can look into it. I don't love them, the options on Spreadshirt that I just saw immediately, but not obviously impossible. Getting ahead of myself, I haven't made the image or put the image on a t-shirt yet. This is the plan. If people are watching this and wondering why the hell is this small Twitch streamer talking about t-shirts, the point is that I want the t-shirt. We did a thing and I want the t-shirt, and on Spreadshirt it's about as easy, I think, once you've got the image file, about as easy to make a t-shirt for yourself as it is to share it so that other people can buy the same t-shirt or whatever. So the plan is that when I get my act together and design this t-shirt for myself because I want it, then I will try and also press a button so that other people can get it too. So it's not me getting too big for my boots and launching a whole merch range. Maybe the selling point or something is that all of the merch is things that I actually wanted for myself. Modulo, you can get it on a hoodie instead, or a dress or whatever, because Spreadshirt just lets you tick boxes for that. Right, okay, learning to do things. Okay. Right, this doesn't sound like it could possibly be true, but let's read this paragraph. The discriminants for which all forms are primitive. Right, yes, we did think about this a little bit last time, didn't we? The ones where you can't do any division before the 10th of August. What happens on the 10th of August? It's a very specific deadline for t-shirt reasons. Squares. This is the other factor of 2. It's not the discriminant of any form. Oh, these are weird. They're reminded of a different one. You could do this, and then there were different cases. Right. Okay. Yeah. Sequence of letters, and there must be in summer school. I briefly signed up for I think one of them, but then it clashed with something else. So sadly, this year I'm not doing any of the NMSSs. I'm doing there's a different summer school that I'm going to, which clashes, which is very annoying. Also, I think one of them is at the same time as A-level results day, but I might be wrong. Maybe next year. Okay. Yes, so we read this. There were different cases for looking for fundamental discriminants. We're interested in the case of whether you can pull out a square and still have something that you could have as a discriminant. So we know all possible discriminants are either 0 or 1 mod 4, and then the question is, does your number have a factor that you could remove that is square and that leaves something that's 0 or 1 mod 4? which, oh my goodness, if you have lots of 2's in your prime factorization, like if your prime is 2, 2, 2, 2, 2, 2, 2, all multiplied together, then you can remove a factor of 4, that's square, and still leave something that is 0 mod 4. So this is the case at the end. And then the case in the middle is if you only have a couple of 2's, so you can remove some 2's. No, obviously no squares over there. Squares over there will be fine because removing an odd square removes a multiple of 1 mod 4, so you stay the same. So if you could make that, then you could make the thing removed, and you could make that. So you could removing the odd primes would be fine. So there's all these like cases to think about. What does removing a square mean? There's different things about removing like an odd square versus removing a even square, because they either change or don't change potentially, whether you're 0 or 1 mod 4. So there's all those cases. In this case, you're just odd, so you've got to worry about removing odd squares, and you've got to make sure that it's actually possible to make this, and then you'll be fine, because there's no squares to remove. In this case, no odd squares, and that even square, you can't remove it. Okay, so I've just got to remember those, I suppose. Definitely don't want 16. Oh yeah, so too many 2's, and you can start removing them. But exactly 3 2's is all right. When you get to 4, you can remove a couple. Crikey. Okay, right. That's a whole thing, isn't it? Let's read this again. Every non-square discriminant can be factored uniquely like this. Non-square discriminant can be factored like this, where this is a fundamental discriminant. Non-square discriminant can be factored uniquely like this. Non-square, you bring this out. Bring out its square factors. And then this bit is square free, I suppose. Oh no, well this is one of these. So up to the 2's. Not thinking about powers of 2, square free. I don't know. So I feel like, right. One way round is something like take a fundamental discriminant, multiply it by d squared, and you'll get a discriminant on quadratic. You could make delta prime, so you can make d squared delta prime. But it's the other way around that they're telling me. They're telling me that every non-square discriminant can be factored uniquely like this, where that is a fundamental discriminant, d greater than or equal to 1. And it's pretty much putting out the square factors, but I've paused a lot because I think the 2's are different. Right, so it depends. Does it depend? So if I have, I'm worried about having like 16 times some odd primes and not knowing whether I'm supposed to pull out 4 squared or pull out 2 squared. Because if I pull out 2 squared, I'm in this case. If I pull out 4 squared, I'm in that case. So maybe it's fine. So that'll be all right. So I just look at whether or not that thing is 1 or 3 mod 4. Is that right? Yeah, depending on the odd primes in delta. Square discriminant. So if it has lots of 2's in, then this says you can pull out. Wow, feels like I've got a choice. It would be unique, right? So I've got to think hard. In the case of like 32n, where I'm stressed about removing a factor of 4. Right. Okay, so powers of 2. Powers of 2. If there are an even number of 2's in your number delta, then, well, that includes both of these cases, but also things with more could be removed via a unique d squared factor, and then whether or not you remove that last pair of 2's in your prime factor to get down from 4n to n or not, depends on whether or not n is 1 or 3. So these are distinguishable. There's some uniqueness here. If I show you 32n, you know whether to, even number of 2's, 64n, then whether or not you go down to saying that that is 64 times delta prime like this, or maybe you say it's 16 times delta prime like this, depends on whether n is 1 or 3 mod 4. So that helps distinguish between those two cases. And if there's an odd number of 2's in your prime number delta, then you either get down to here, or if odd number of 2's, then you remove 2's down to here. you don't remove the extra factor of 4 because that would give you a number that's 2n with n odd. And that can't be made as a discriminant of any form. So you have this choice between possible and impossible, which is nice, I suppose. If that was possible, removing another factor of 4 would not give a fundamental discriminant because there aren't any of the form 2n, because there aren't any discriminants of the form 2n where n is odd. Crikey. Okay, quite a lot to think about. Okay, deeper properties in later chapters has been underlined as an example of this book advertising future chapters. Okay, class number is always a multiple, and there's a not too complicated formula for this. Multiple is fun. Okay, but we're not going to do it. Okay, good. So here's the star for where we got to. Good old 20-minute warm up. Oh, it's 4:20. That's an exciting new feature of starting the stream at 4 o'clock. All the times are different. Good. Okay. Right. Discriminants of class number 1. These are ones where there is only one quadratic form, really, up to proper equivalence, but proper equivalence is a bit more strict. So even if there's only one equivalence class, then it's not even the case that you like have a pair that are the same under reflections or something. There's only one equivalence class here, which it would be nice because if you spot the discriminant is some number, you can say, well, up to transformation, I know where I am. So this would be very nice because helpful, because knowing delta is sufficient. So if you find the discriminant of your quadratic form, and it turns out to be minus 163, then I'm told, well, that's unique. So maybe there's a table of these that you can look up and say, aha, I don't have to think anymore. That tells me that it's exactly my favourite one with discriminant minus 163. Which, what is my favourite one with discriminant minus 163? I suppose probably x squared minus 163 y squared. Does that work? No. Oh dear, it's of the form 4n plus 1, isn't it? So I should think about 4n plus 1. So I should think about this. 4ac plus 1. So this has got discriminant minus 163, I think. 1 minus 164 is minus 163, and up to what am I talking about? Up to transformations. The sort of transformations that move. What sort of transformations am I talking about? In my head, they're Mobius maps, but they map complex numbers to complex numbers, so I should maybe interpret that. But ones that rotate and pivot and move around the fairy diagram of the fractions, points xy, pairs xy, that's the only one. So, questions about what numbers it can take would be answered by knowing what numbers this one can take. If that was the question. That's closely related, I think, if you've seen this polynomial, which generates quite a lot of primes. I think they're closely related. I don't know why, but it's the sort of thing that I think I've been told before or something. Because there's an example. Something nice. There are 4 more discriminants which are not fundamental, where we've multiplied these by some square. So choose a square, like 4 to get 16, 28. Why not 32? Or maybe they don't have class number 1 or something. Not obvious. Why can't I have 44? What's going on? So it's not just these times a square. We're missing loads. Okay, so maybe I'm being told that these also have class number 1. No other negative discriminants. Wait, what? Oh, right, okay. So this is known recently, 1950s and 1960s. This is it. This is a total list of ones where, oh, these I liked these ones. This is a total list. That's pretty cool. That gives a wow. That's it. Otherwise, there might be there are quadratic forms of other discriminants, but you can't. You have to do more work because the equivalence class is if there's more than one, then identifying which one you're looking at. Wow. I didn't need a little face. I'll see the face. Another result from the 1930s. No. Oh, hello. Hello, good to see you, Alex Mayo Hugh. You're stuck on discrete maths. I don't know who Kimberly Brem is. I don't know who that is. If you've looked them up and they've got videos about discrete maths, then maybe that's helpful. You could check them out. If you're trying to get me to type that into YouTube, I'm not going to do that now. But maybe somebody else in chat might help. If other people in chat know about discrete maths, they might let you know. If you want to ask us a question, we can maybe help find stuff. But I'm going to carry on learning about discriminants of quadratic forms. Good. Right. Okay. Welcome to the stream. It's pretty chill around here. We really might help with discrete maths if you want a particular thing done. But my default is that I'm going to learn this. Well, what am I learning at the moment? Who knows? I'm just being told that things were proved in the 1950s and 1960s, but who knows? Okay. For each number n, there are only finitely many negative discriminants with class number n. Oh gosh, okay, so this is the case where 1. This is like telling me the table the other way around. So, something like, for each number I'm quite interested in what its class number is, because that tells me roughly how hard it is to determine what quadratic form I'm looking at. But then the fact here is reading the table the other way. So I've got a table or maybe a function or something that says something like, you give me the discriminant, you look up, you find the kind of function. I guess it's dot-e because we're on the integers. But you give me a discriminant and find me the class number. This is like a fact about a kind of inverse function, not a function, but it says that going the other way, if you give me coming in this way, a class number, there's only finitely many points that take that value. Did I need an inverse function? Not sure. And it's been done for up to 100. So that's progress then from doing it for 1. To know which numbers give you class number 1. And you go as far as about 100. Good, okay. But 1 is maybe harder. Oh, for positive. I missed that. This was the word. Where's the word negative in here? Oh no, that's because we were talking about elliptic forms, which have negative discriminants. Positive discriminants for class number 1 is not as well understood. A large number of positive fundamental discriminants for class number 1. Likely to be infinitely many. Don't know. Unsolved. Fun. If one allows non-fundamental discriminants, then it's known there are only finitely many. Wait, what? If you allow more... no, sorry. It's known that there are infinitely many. I missed that. Including, for example, discriminants like this. Ugh. They have... Okay, so they're not fundamental because you can take out square factors in a kind of obvious way. Yeah. Take out a factor in kind of an obvious way. If the discriminant's got a square factor, what am I saying? If the discriminant's got a square factor, does that necessarily mean? I'm saying that like it proves that it's not not primitive, but I guess I should actually think about all of this complicated stuff at the top, where we've looked at the different cases. And in all of them, I want the odd part to not have a square factor. And here, in that big power of 5, the odd part very much has a repeated factor of the odd prime 5. And in this 2 case, it's subtly different, isn't it? This is just too many 2's. So it's not. I shouldn't talk about the parity of the number of 2's. I should think about the number of 2's in the prime factorization and the parity of other primes. 2 is a very odd prime. In each case, all forms are equivalent. For example, when you have -163, you do this test, you find these values of h, and then we could go back to this. We did this a little bit of this a while ago. Corresponding values all happen to be prime. This forces a to be 1, but since h is less than or equal to a, this means h must be 1, and we just get this quadratic form that I did manage to write down on the previous page, lucky me. Prerequisites. Depends how much you want to do. I'd say a lot of it is pretty prerequisite free. There's some sort of algorithm stuff where it might just make sense to you. Depending on what you want to do with it, though, I'm vaguely aware of things that get much more complicated, but it's not like a research area that I know very much about. So if you just want to understand about, I don't know, Dijkstra's algorithm or something, then in some sense just go for it. Just find out about Dijkstra's algorithm. As for CS, yeah, I think you should just go for it. I think when I did a little bit of discrete maths in school, we learnt it without learning why any of the algorithms worked. We were just taught to implement algorithms, and for that you really don't need any prior knowledge to follow the instructions. In your case, if you're doing it for CS, maybe you might be teaching it to a computer or telling a computer what to do with the algorithm. Hopefully you get to understand it a bit more. Hopefully you get to actually look under the bonnet and see why it's working. But it's not going to use, I think, to get you started, it's not going to use like calculus or weird number theory or even quadratic equations or anything. I think probably to start off with, you're making logical choices at each step. And there's some sort of reason, perhaps, to justify why the thing works. I'm trying to remember off the top of my head how Dijkstra's algorithm works, because now I've mentioned it. So now I feel like I have to talk about Dijkstra's algorithm. Good luck. Is Dijkstra's algorithm one of the ones that you have to do? Is that something you have to know about? If you've got any examples of the sort of discrete maths that you might be doing? Yeah, it can probably mean different things to different people. I should be careful because I learnt one set of things for one particular course. Maybe your class is totally different. Who knows? Other people in chat, have you learnt any discrete maths? What does discrete maths mean to you? Engagement. Possibly they're learning things in school as well. Who knows? Or out of school, or class, university, general life. There's loads of stuff around, isn't there? Twitch. The place where we learn all of our discrete maths. You have to be careful what you say, right? Because some of it's extremely hard. So I shouldn't give the impression that all of discrete maths is really easy, no prerequisites, don't need to know anything. Yes. I don't want to sell it short. Right, good, okay. Oh look, here's this prime fact. Hey, thanks for the follow. This is getting us closer towards our goal of having more followers than there are numbers on Wikipedia. Maybe not strictly more, but 315 is the smallest number that doesn't have its own Wikipedia page, at which point we've finally got into the interesting numbers about which not much is known. Sorry, I saw myself in the camera monitor beaming down the camera claiming the number 315, of which not much is known. Got myself. Sorry, here's the prime fact. I love this prime fact, it's good, isn't it? Plug in the numbers, you get primes. And maybe you think, will it always give me primes? And this is a good question for teaching people about patterns and teaching people to not just check the first few cases, because no, it's not always primes. Here are these 40 primes. Nice. What's going on then? There's excessive differences between these primes. If it tells me that these are just in the topograph or something, that we can just like, ooh, look over here. That'd be amazing. That'd be great. That would be good. Notice that the excessive differences between these primes are even numbers because it's a quadratic expression. Since, yes, do the algebra, good. The next number in the sequence after this would be that, which is 41 squared. No, okay. Yep, plug it in. A similar thing happens for all the other negative fundamental discriminants of class number 1. Shame there's only finitely many. Non-trivial cases are listed in the table below. We're going to have a look at the table, and I'm going to read that chat message. What does this say? Oh, look, here's some strings of primes for you to look at. So we have the fascinating fact that for d equals 7, you get, I had to learn this slowly, but not 7 here. You get about 1/4 of 7. The rule is it's about 1/4. 1/4 of d plus 1. That's what you write there, so that you end up with d plus 1 over 4. Yeah, 1 minus 4ac. b squared minus 4ac in each case is, if I got it right, well, plus or maybe minus d. Something like that. Right, the chat message said, do you think the current state-of-the-art AI models are good at explaining, not solving, in a dumbed-down way, uni maths? Yeah, I think they're all right, actually, for explaining. Some of them are doing a little bit of solving, perhaps. Don't use them for your homework for uni, I would say. Maybe as a starting point, but don't. Something I enjoy is not bullying ChatGPT, but putting ChatGPT in tricky situations where you can ask ChatGPT to prove that something is prime. I was learning about Gaussian primes or something, so I said, can you prove this thing is prime? And it did it. And then I said, can you prove it's not prime? And it did it. And it was kind of convincing both times. So when you say, can it explain things and solve things, like yes, but dangerously so. Make sure that when you ask it to do things, okay. When you ask it to do things, it will do it. So if you're asking it to explain something that's not true, it will still do it. If you ask it to help you with a homework problem that's ill-posed, then it will just keep going anyway. That's my experience of getting AI to try and explain things. Just be like, oh, there's a number on it. I'm like, is it prime or not? It would tell me it was, and I was pretty sure it wasn't, so I got it to tell me it wasn't, and I said, oh yeah, okay. Proved it the other way. Quite malleable. So do be careful. If you have any biases, it will reflect them back to you. Right. Yeah, you can't be mean to bots. Totally out of character. Right. Yeah. I think it's quite good at being, if you need it to explain. So I've been trying to learn about to do small things with Python, and 10 years ago the healthy thing to do would be to read a book and think carefully about Python basics and build up from basics. But I've decided I'm never going to learn Python basics. I'm just going to jump straight in, copy bits of code from the internet, see what happens, adapt them to what I need to do. And there's now a big shiny tool that takes bits of code from the internet and adapts them a little bit for me, so maybe I don't even need to think about that step. Just decided I don't know how Python works. Maybe I'll never learn. I might pick it up over time, but in a way, modifying other existing things is just so much easier than trying to learn the basics. It's probably not healthy. If you're watching this, if you're in uni and you're learning about CS, maybe learn to do it properly, but maybe learn what's actually going on. It's probably good for you. I've decided I'm not going to. God. 4 p.m. James is not a good role model. Right, okay. Do you need a bachelor's in maths? Oh yeah, with the yeah. No, that's what I mean, right? Did you hear the story about where I got with all of the internet and LLMs, and I asked it, is it prime? And it said yes. And I asked it, is it not prime? And it said yes. But yeah, bachelor's in maths has been quite helpful in terms of understanding and checking whether things are nonsense or not. I actually think identifying true statements is going to become more and more valuable as the world fills up with statements. There's going to be a lot of stuff around. Knowing which things are correct for yourself is maybe going to be important. Right, okay. Satisfactory explanations. What is that sentence? Are known for the occurrence of so many prime values of quadratic polynomials, but they involve fairly deep theory. Aww. It's curious that the list of prime values account for all primes less than 100 except 79. 79, mysterious prime. That's my bingo call now. 79, mysterious prime. Right, bingo. Okay. Right, what are the next 40 values? Okay, so there's 41 squared. Whoops, bit awkward. You put 40 in, you get, yikes. not a prime. The next value when x is 41 is also not a prime because it's a multiple of 41. I mean, come on, you put 41 in here, you get a multiple of 41, a multiple of 41, and then the number 41. Good. After this, the next two values are primes, but then something that's not. Ooh, nice. Then 4 primes, then this, then 6 primes. No. I don't like this. I thought this was just going to be a story about how it's not prime, but worse. I think they're trying to tell me that it goes in a predictable pattern, whether or not it's primes. Next two values are primes, then non-prime, then 4 primes, then 6 primes, then 8 primes, then 10 primes. And then the next 4 values are prime as well, completing this next second 40 values. Interesting. But then the pattern breaks down. Okay, and it's broken down at something that involves the number 163. Don't love this. Before the breakdown, not only were we getting sequences of that many primes, but the non-prime values were the products of 2 successive terms in the original sequence of prime values. Right, okay. Maths is ridiculous, isn't it? Maths is just crazy. It's very hard to know where you are with these interesting properties of finitely many numbers. It's a little bit like the Wikipedia page for the number 315. Right? It's interesting properties of finitely many numbers. This is a nice pattern, but it can't generalize infinitely much because 163 is actually the largest negative fundamental discriminant, I'm told. So we can't go anywhere with this. And yet, satisfactory explanations are known for what's going on for this particular number. I think my bias is I like it when things are true, for all n, or for all primes, or for all discriminants, and I feel uneasy when things are true for 163. Here are some more facts about the number 163, which is my sort of personal bias, right? That I'd like things to be like, oh yeah, you want 1,000,000 primes, go and look over there and you'll find 1,000,000 primes. Whereas this one says, you want 2 primes, then 4 primes, then 6 primes, then 8, then 10. Woo! There it is, which is a bit more like bespoke. What happens after that? What do I think happens after that? Probably before the differences were the even numbers, and then the number of primes we got were even numbers, and now the differences between the primes are something to do with the previous sequence in terms of their multiples. They're multiples of this. So maybe the next ones will be multiples of that. I don't know. Should we read on? Oh, they don't continue forever. Oh, okay. Right, the polynomial does that. Ooh, that's a good fact. I like that a lot. Should we check that? It says easily. Maybe the stream is chill enough that we can check this easy fact or something. Easily check that. So it's telling me if you add 40 to this number, then it's the product of some of the things you've seen before. Well, let's check it by just plugging in everything we can see. So 40 plus n squared, I'm going to plug in over here. This is going to be p of 40 plus n squared. Sorry about the vertical line for the page edge there, which is going to be this much. 40 plus n squared plus 41, which, my goodness, that's quite a lot of number, isn't it? It looks like n to the 4, so equal signs. Be disciplined about this. 81 n squared if I bring in this one as well. Not bad numbers. And then 1681 if I add those in. Okay, whereas, and Pn minus 1 Pn is equal to n minus 1 squared plus n minus 1 plus 40 multiplied by n squared plus n plus 41, which is, right, how do I want to do this? I think I'll simplify this first bracket first. Minus 2n, so minus n. The ones cancel and I get 40, which is looking good on that constant over there, 1681. I can see that's going to work out because, oh, is it? No, I've screwed up somewhere. Where have I screwed up? 41. That's where I've screwed up. Oh, I've rubbed it out too much. Minus n plus 41. I suppose there's a 1 here, a minus 1 here, and a 41. Oh, that's the difference to 2 squares. Oh, maybe I should have spotted that. Oh, what's going on? What's really going on here? What's really going on here? I mean, let's just multiply it out. N squared plus 41 squared minus n squared. That's 4 plus 82 n squared plus 1. So 41 squared is 1681, but minus n squared. So this does check out. What's actually going on there? I mean, that's the algebra. What's the thinking? Not sure there is any thinking. There isn't always. So what does this mean? Then you get up to 40, then these things are going to stop being prime or something. If you add n squared, so these are the ones with even differences. Ah, right, okay, this is good. Right, I see. So these even, we saw 2 primes, then 4 primes, then 6 primes, then 8 primes. And the composite ones there are perhaps composite because you can factorise them like this, with these larger and larger gaps. So 40 plus n squared gives you larger and larger gaps as you increase n. Okay, I see what they're saying. This is telling us that these ones with increasingly large gaps are not primes. Do some of these factorise further? I mean, no, because these all look prime because the values of Pn are all prime up to a certain point. So surprisingly, they're semi-primes. They might have factorised more, but they don't. It doesn't explain why the intervening ones. Okay, it should be prime. Fair enough. Okay. Right, I think I should actually do exercise 1. I usually skip the exercises, which is bad behaviour. I think I should do exercise 1 and then think about some symmetries because I love symmetries. And it's going to be awful. Here we go. Oh my goodness, right. I don't know at all how I'm going to do this. Because I don't think I've understood how to find the class number. Have I? No, I don't think I have. They could even catch me out by doing a thing here that's not a multiple of 4 and not 1 mod 4. Is that what's going on over there? No. These look like 92? No, yeah, good. 87? Interesting. Yeah, okay, these look like they've been kind. And all of these are 1 mod 4 or 0 mod 4. So I think all of these have at least 1 for their class number. I don't believe I can calculate this, right? Oh, do I do the whole calculation to say start finding? Yes, it's a big calculation, right? It's a big calculation because I'd have to go h squared less than negative delta over 3, I think. So let's start by looking at 23. Quick cheat, I'm going to have a look back at this list to see is 23 going to be one of these ones. Minus 23 is not one of these ones, so we should get a non-trivial answer. That'd be, I think, worth doing. Okay, so I think I'm just going to do 1A. Don't always do the questions. In fact, I always don't do the questions, but here we are. Right, okay, what are we doing? 1A. So here's what I remember. What do I remember? I remember that h squared is less than or equal to delta over 3, and I remember that, what's this then? That's the value of h, and something about 4ac. What do I know about 4ac? I'm going to have to go back a bit and find the thing about 4ac. This one. This one. 4ac is minus delta plus h squared. So I think I'm going to put minus delta here. So delta is minus 23. I'm going to put a minus sign there. And minus delta is... Which way around was it? Was it this way around? H squared plus 4ac. No, it was the other way around. (4ac) equals h squared minus delta or something. Okay, so if delta is minus 23, then I've got some cases to look at. If delta is minus 23, here are some cases. H squared is less than or equal to 23 over 3 is 7 and a bit. 7 2/3, so H is... do I need to get the sign of this right? Oh, there is a parity thing, isn't there? We'll discover that in a second. I'm going to think about 0, 1, 2, but I can't go as high as 3 because I'm going to be that large. I don't want to think about negative H right now. And then I want to think about, yeah, so this is the discriminant fact, right? It's H squared minus 4AC, where H is what we're using instead of the middle coefficient. We're thinking about the coefficient HXY plus CY squared for some reason. I suppose that measures the difference between the two. It's fine. It's not the value, it's the kind of difference in the arithmetic progressions of the values. We've been there before. Right, there's a reason you might write H for this. Crikey, okay. Which means that, now since 4AC is a multiple of 4, and in this case, you'll notice that this is odd. Better be the case that H squared is odd. So 4AC, now this fact, so H is 1, so that we get a multiple of 4 on the left, well, a multiple of 4 on the right, sorry, when you plug in H. So it must be the case that AC is the number 6. And there are a couple of ways to factorise that, aren't there? I've got some inequalities though. What order are my inequalities in? Is it H less than or equal to A less than C? Good. I think you can rearrange. If not, you could do a rotation or something to get it into an equivalent shape. Okay, so A's got to be less than C, so I could have HAC could be 1, 1, 6, or HAC could be 1, 2, 3, a pleasing sequence of numbers. Okay, these have got the same discriminant, but they've got different values, I think. Let's have a look. So the values A and C, so in the first case, x squared plus xy plus 6y squared has got values, well, when you plug in, let's put a line down the middle, when you plug in, so there's two big regions here, 1 over 0 and 0 over 1. Which way around do I want those? Probably this way around. Plugging in x over here, you get 1. Plugging in y equals 1, x equals 0, you get 6. And then over here, we've got the bit where you plug in 1, 1, and you get 1, 2, 8. And over here, you plug in 1 minus 1 in some order. It's minus 1 comma 1, and you get 1 less. Doesn't matter. Flip both signs, you're okay. So 2 less than the thing I just wrote down. 6, I think. Let's check that in some sort of Desmos tool. Don't worry, I'm loading it. Desmos tool from Maths222. So Maths222 is Desmos Whiz in chat made me this, which helps me evaluate a quadratic form on all the fractions. The fractions around the outside, there are all of them, only some of them are shown. But it's a tool for evaluating quadratic forms everywhere. Did I get it right? Oh yeah, so 1686 is the bit I've recognised. And then if I keep going, I should find more things. But I think I'll stop there for now. 0 on the right, good. Okay. Something about source edges. So I would like to check that these two are not equivalent. I can't remember if we've got any technology to show me that they're not equivalent. For example, so then 2 is the amount that you add to both of these. So it's the difference in this, you know, the arithmetic progression goes 6, 1 and 6 make 7, and then 8. You have to read across this split shape, reading the bit on the left and then the bit across the middle and then the bit on the right, wherever you see this kind of, what shape are we calling that? I don't know, four-legged stick thing. Okay, so in this case h is 2, so I expect up here instead of 4 I'll get 6, and down here I'll get 2 when I plug in those values. So I'll give that a go as well. And it's got the same discriminant. Yep, it's got the discriminant 4 minus 4 times 3 is 12. What am I talking about? What have I done? It hasn't got discriminant minus 23 at all, has it? What have I done? Ah, I've mixed up A and C. Right. Yeah, I got away with it before, but I've mixed up A and C. A and H, maybe. This one. Different numbers. So I'm supposed to have A over here, and H should be 1. So then I get 2, 3, and then H is only 1. H is 1 again, H has to be 1. So 5, 6, 4 down here. Okay, so 6 up here, 4 down there. The difference across here is 1. Which way around do I do that? So if you write the thing, if you draw an arrow for increasing direction, then you find a source node in this case where reading across here you have 3, then 6 across this edge, and then a 9. So we're going out that way from this node. And going this way you have 2, then 7, then 12, so it's going out this way. And then I think it keeps going outwards from there. So sort of from this point outwards, the numbers get larger. That can help us identify that these are not the same thing. So if I keep H as 1, but go back to look at this one again, this one has got, so again, this edge, numbers are increasing as you go from bottom to top. 6, and then the average of these, or the total of these is 7, sorry, and then 8 up the top. And if you keep going outwards, it'll keep getting larger. Going out this way, it goes 6, 7, 8, and going out that way, it goes 1, 12, 23. Ooh, 23. So again, we've got this kind of source vertex. I'm drawing some arrows on my diagram in here of things going outwards. I think that point's unique. So I think these are not equivalent because you can't transform one to the other. Then I've got to think about reflections. Because I'm supposed to count the proper equivalence classes, and this one has got a reflectional symmetry. This one doesn't. So the mirror image of this one would be morally about the same, but properly it would be different. So I get 2 equivalence classes here. So I think H23 is 3. I think. And now I'm going to look up class number for 23. Ah, right, here's a website. Yada 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 yada. Oh look! Oh no! Let's read this. This looks very nice. And it's got the numbers in, including the ones where you have 1 and 23. They say 3. Brilliant. I'm just going to read this to see if it's a different definition from the thing I've been doing. Only finally many equivalence class positive definite binary quadratic forms of discriminant D. Since there is exactly 1 reduced binary quadratic form in each equivalence class. Suffices to show that there are only finally many reduced forms like this, and then that. This is different. I've got a 3AC in this one. So if you look at this table for other ones, this goes up to 839, so that's quite fun. Each number on the right only appears finitely many times, I'm told. So there's a few 1s to start off with. And then, oh look, 10. And a few 10s. There's still a 1 there at 163, but I think that's the last one. And then onwards. some more 10s. Still got some ones where there are 3. I think we might have run out of ones where, oh no, there's one here with just 2 equivalent forms. So it's not really a sort of simple pattern for these numbers at all, is there? 26 for that one, that'll be really confusing. And I can't see any more 2s in the right hand column at the moment. And keep going, loads of those, lovely, and then stop at 839. Okay. I want to know about proposition 2.1. Oh, right, just go and do it. So what's this saying? So they're using ABC, which I kind of prefer, because I have to think about H labels on the topograph. ABC, just the number B as the coefficient. If it's reduced, then this is true. Okay. Yeah, I think it is that time, isn't it? It's 5 o'clock our new tea time. If yeah, that, okay. And then b squared less than a squared, because b is less than a, and then okay, a is less than c, so that's true. So b squared minus 4ac is less than minus 3ac, and that is what d is. So minus d is greater than or equal to 3ac. Only finitely many a's and c's to do this. Yep, alright, okay. Tea time. If you're new here, then what we do halfway through a stream is I go and make another cup of tea. So I'm going to make a cup of tea now. You are welcome to make a cup of tea as well. If you hang out here, then you'll see it say back soon on screen, or maybe you will see an advert because I'm going to click that button as well. Either way, I'll see you back in a couple of minutes for more stuff to do with class numbers and a cup of tea. Yep, right, okay, back soon with tea. See you in a minute. I'm back, hooray! Oh, with a cup of tea. Everything's going to be good. Look, I'm now confident that I can do some more class number calculations. I mean, the first one was the answer was 3. I had to think. If I do a couple more, I can check my answers on this page. That's the plan. Thank you for the tea break, Mary. Right, yes, okay. Stack that over there. Let's do another one. So, same, but minus 47 instead. So, what am I going to do? I think I'm going to do it in the same place. So we're going to remove all of this. Cut. I'm going to remove all the 23s. But I'm going to try and do the same calculation. And find these. Okay, so now B. Okay. So we're increasing this, which increases this number in here. 47 over 3. Let's put this in here. 47 over 3. The hardest part for me is working out that this is 15 2/3. Because 45 is 15 threes and then 2/3. Good. So not quite 16. Now you'll have noticed that this is an odd number again, so I only want odd values of h. Let's see if I can go faster. Not as large as odd values of h, James. Not as large as 4, so h could be 1 or 3. So we have h squared plus 47 today. So we must consider the cases where for AC, so AC could be equal to, if h is 1, then we have 48 divided by 4, you get 12. Or AC could be, if you have 3, 9 plus 47 is, how did I get into this position? 9 plus 47 is 56, divided by 4 is 14. We get loads of factorizations for this one, don't we? So in this case h is 1, so I'm interested in HAC being 1, 1, 12, or it could be 1, this is fine, or this is fine, but actually I've remembered that A has to be less than or equal to C, otherwise we switch, which I suppose I am interested in for symmetry. I suppose I'll look at the symmetry and I'll spot that later. And over here we have cases where H is 3 already, so actually this isn't going to lead to any cases, has it? Because I haven't got any factorization 14 that use large enough numbers. We've moved to 4 o'clock, and I think it is a permanent switch. So it's now 4 o'clock stream, Chill Maths on Sundays. Lifetime? Yeah. I've started driving lessons. And the driving lessons are also on Sunday afternoons. So now my pattern is driving lesson followed by streaming, hooray, learning to drive and learning the class numbers of quadratic forms. Which of those will help me more in my life, who can say? But Sunday afternoons are now highly educational for me. No, I'm not streaming the driving lessons before anybody. It doesn't become an on the road thing. Oh, so there's the switch between heartbreak from Mary and yay from Boom and Will. Ah, maths do is learning to drive too. Hooray! I am not good at it, but we'll get there. That's the point of learning. It's like that with quadratic forms as well. I'm not good at it. Right, I can't think of any numbers AC which are both larger than 3 that multiply to give 14. So I think this one was nope. So I found these cases, and then I'm supposed to evaluate them, which I will get faster at, but for now I need to draw the diagram to say that's 1 and 12, A and C, 1 and 6 for A and C, 2 and 6, read the correct values, 3 and 4 for A and C, and then H tells me how much that sum changes. So in the first case, H is 1 in all of these, so 13, so I wrote 14 and 12, in this case 8, so I write 9 and 7, H is still 1, so 7, I write 8, and 6 for 6, 7, 8. We've got this rule. Non-drivers. Oh, yeah, okay. Oh no, do I count? Oh, I did one lesson. I've been so proudly not a driver for ages. Oh no. Okay, so this one has, I think, one class. This has two, and this has two, I would say, because there's no repeats. And it feels like it's always the case that so in this case, I have these source nodes again, which I think might be because we've set it up properly, that this happens down here. H is positive, and I'm putting this thing up here. So I'm working my way up. And then there's some possibility I get the same number around here. Or possibly that H could, if H is 0, then I get the same number above and below. I get a symmetry like that. But I think that 47, or possibly I'm supposed to write H of minus 47 here. I'm not sure. Not sure which one to write, but I think it's 5. I suppose minus 47. It's a discriminant. I think it's 5. I'm looking down a lot to write. That's not great. Not great, Twitch. Yay, 5. Hooray. Calculating slowly. We're going to do a couple more just because I've decided that I want to get good at this. There's some patterns that you get down here that I haven't quite understood yet. So 71 is another odd number. So we will again be looking for odd values of H in this case. And there's some patterns down there. I think this time round I'm interested in what I get at the end, and thinking about the precision, a more precise statement of the fact about having a reduced form means that I tend to get a source node down there. Right, could have been Formula 1, couldn't it? Hello, Herb, you alright? Good to see you. Welcome to the stream. At our new time of 4 o'clock on a Sunday. It's later in the day, it's even more chill. This was making me much worse at dividing by 3, for example. What is 71 divided by 3? Horrible question, horrible question. Is it about 20 something? 23 2/3 or something? This is terrible. It's 3 24s would be 60, 72. Yep, good. Okay, I'm forced to divide odd numbers by 4. By 3. Don't like dividing odd numbers by 3. It's not a rational opinion to have, is it? Hooray! Ah, more chances to get some rest. Hello. Hamiltonian Dynamics has followed. Good to see you. Great username. One of the all-time ones. And just after we mentioned F1, so nice to see another Hamilton fan in chat. He's so good at those dynamics, isn't he? I'm also aware of the Hamiltonian dynamics maths thing. Tee hee. It's good that they're both good at dynamics, though, isn't it? Right, good. Okay. Ooh. Fine line between funny joke and genuine idiot, which I have to play with quite a lot, right? Okay, time for me to list odd squares that are not as large as 23 2/3. Will I pull that off? If not, perhaps it's my walking the line between comedy and sincerity. There we go, just 1 and 3, I think. Positive numbers that square to something that's less than 23 2/3, and they're odd. There you go. Thank you. Your version's better. I prefer your version of that. Right, 72 divided by 4. Oh, now I've got to divide by 4. This is hard work, isn't it? Is that the one that's about 18? That's the one that's about 18. So when H is 1, you have AC is 18. And maybe this time we will find some solutions over here. Maybe we're slowly building up. The first case we had one solution. There was only one value that H could be. The second case we had 2 values of H, but one of them didn't lead to any solutions. Maybe this case we will see some solutions. Oh gosh, there are like 6 or 7 of these, so learning, including some even numbers coming up over here. We're currently here. Oh, right. When H is 3, I add 9 over here, I get 80, so AC has to be 20. The catch is that both numbers have to be at least 3. 20 is not a multiple of 3, but I am going to pick up a solution. 4 times 5 is 20, with the numbers in order. So HAC could be 3, 4, 5. Right, okay, over here, we're trying to categorize. If you've just joined us, we're trying to categorize. What are we trying to do? Count the quadratic forms of a particular discriminant. In this case, the discriminant is -71. And there's only finitely many of these. They would have h squared minus 4ac equal to -71. But after doing some transformations, it might not be true that literally the numbers in your quadratic form look like this, but it's equivalent to one where the numbers are kind of small and in this order, and this strictly limits the size of h squared. You can prove that h squared is less than or equal to this over 3. Maybe I should redo that just to convince myself. Yep, time out, quick break. We're going to try and remind ourselves of why this is true. So we want to show, oh, that's the pen toggle there, isn't it? We want to show that h squared is less than or equal to, and I'm going to use the definition of this as h squared minus 4ac divided by 3. And this is because, so sufficient would be if we could say that h squared was less than or equal to 3ac, moving this around, 3h squared, 2h squared, and 4ac. That's the definition of negative delta. Well, have I got the minus sign? Not sure I do have the minus sign. I didn't have the minus sign. We want to show this, which is the same as saying that h squared is less than ac, which is just true because h is small. So proof, something like, oh, I just saw this before the break, didn't I? It's less impressive if I've seen it before the break. H squared is less than or equal to a squared because h is smaller than a. And positive, I think. I'm only thinking about positive h. Zero. I'm going to put a 0 in here. And then that is less than or equal to ac because a is less than or equal to c. So where do I want to put this? So 3h squared is less than or equal to, what am I doing? So 4h squared is less than or equal to 4ac. So, and then h squared is less than, take one of them over to the right hand side and divide by 3. Done. Good. So using all of the available facts, we get this bound on h squared, which is really handy if you're trying to find all of the possible values, because we've got an upper bound on the square of h now, which is this 23 2/3 number in this case. Hooray! Right, so there's lots of cases over here though where this is going to give me actually loads. And then I need to check them for symmetry. Maybe not that many. I might have overreacted because I need a less than or equal to c. So HAC, I have to stop here because although 18 is also a multiple of 6, I have to stop at the square root of 18. And then think quite hard about the values that I'm getting for A and C, A and C, A and C over here, A and C, and the value of H tells me how much the sum changes as you move from this value to this pair of values to this value. I'm saying sum, but it only applies to the sum in the middle, I suppose. I haven't found a good way to describe this fact. The fact is you add these, you get 19, and then you write 20 and 18 here, the difference being 1. The rule for this one, where H is 3, is you add them, you get 9. You write 12, which is 3 more than 9, and you write 6, which is 3 less than 9. We're looking out to see if we get any like mirror symmetry, like we get 18 on both sides of this line, because that only gives us one class, whereas this one, so 10, I write 11 and 10, 1 less than 10. Ooh, do I use, no, 1 less than 11, 12, 10, and 9, I get 9 plus 1 is 10. Oh my goodness, welcome back to Twitch, where 9 plus 1 is 10. Sweats. Chat sets chat to emote only mode. I need to add some small numbers. Chat, let's go. Oh, we do have emote only mode. Could try that in a second. I think chat would be quite good at emote only mode. Okay, so 1 character there, 2, 2, and 2. So I think that this might be 7 in this case. I've got a big list of these on my other monitor. Let's have a look at the big list. 71, 7. Hooray! I just thought during a kind of this kind of like long calculation where it's just me trying to like knuckle down and do something, like maybe I should set chat to emote only so that I don't get any hints from chat. Actually, yeah, chat's very nice, so maybe I don't need to do that. Also, do we have enough emotes? We have oh no for bad time. We should have a good time. Okay, next one. We're going to set delta to negative 87. And I'm going to have to do things like dividing 87 by 3. Let's just think over here. Quickly think over here. So in this case, h is equal to... What is this? So this is a plus c minus h. And it's equal to, shock horror, c, because a is equal to h. So I think that's predictable. I can see that happening. So I might try and shortcut that later. I might try and shortcut that if it happens again. And I think it might, because odd number is going to admit, large odd number is going to admit h equals 1, and then whatever I get from my multiple of 4, I'll write down 1 for that one. So I think I'm going to get at least one case where there's some symmetry and I only get one class. I don't think it's going to happen again though, because if I have different numbers, I don't think this can be equal to c, for example, unless h is equal to a. It's the same thing. I don't think it can be equal to a unless h is equal to c, in which case it would also be equal to a because of the sequencing. So I think I just have to watch out for cases like this, where they're equal. I think I'll write 1, 2, 2. Not equal, so 2, so 7. That's going to be my shortcut. We're going to see if it causes disaster. Disaster will result in the oh no emoji, I guess. And also because for chaos reasons, oh, I've done something. I think I've changed page. Yeah, wow, we've changed page massively. Where have we gone? Where are we? I don't think we're in Kansas anymore, Dodo. Let's clear that. Oh, here we are. Okay, good. We're back. Okay, so delta is minus 87. Discriminant is minus 87. It just went back like 10 pages. It's crazy. Chat. You can't see it, I think, but somebody is trying to sell me something. Let's just ban them. Good. I don't think you saw that. Did you see it up there? I can't even tell. I should look up there and see if you see it at the same time. Just doing some chat moderation. You can't see it. You can't even see it on screen. We're good. Oof. Just doing like 3 jobs at once. Right. Or you know what would prevent them from doing that? In my only mode would prevent them from doing that. There you go. Let's see what that does. Right, okay, here comes the calculation. For class number of minus 87, chat's not allowed to help. They're in emote only mode. We haven't tried this before. We're going to see what that does. I think they're allowed to use emoji and things. I'm not sure. Let's find out. Twitch, what does that do? Yeah, that's a pretty accurate start. Off we go then. Good. Okay, this is minus 87, so I need to divide that by 3. Ooh, for the first time, they've given me something that is a multiple of 3. That's exciting. I'm trying to write in selecting tool 19. So I need, again, because it's an odd number, I need odd squares up to 19. So I'm going to write h could be 1, 3, not 5 yet. Stop. So what I think maybe this time what we're going to see is multiple things splitting. Let's see if that happens. They are allowed to use emotes generally, maybe not emoji. They're trying to work out how they can tell me that they can't use emoji without using any emoji. Possibly just oh no. Who can say? Right, okay. When h is 1, then I have to factorise over here. Divide by 4 is 22. So I get cases like 1, 1, 22, and also cases like 1, 2, 11, but then stop, to which the number of classes is 2 and 1. But then in the 3 case, possibly I'm going to see a case with 3, 3. That would be great, wouldn't it? So 9 more than 87 is 96. 96 divided by 4 is 24, which is a multiple of 3. It's happening, chat. As we called it, 3 times 8 is 24, but there's also this case 3, 4, 6. So I think that this gives me, oh yeah, sorry, I've put my, that's wrong. I think there's 1 case there, 2 classes there, but only 1 class there and 2 class there. So I think the total might be 6. I think. Let's check the big list. And it did the splitting. So this case is different. There's a sequence to these. This case is different because the thing happens twice. That there's some symmetry. It's this 3, 3, 8 thing. So A is 3, C is 8, so those are the values left and right of the middle part of the top graph. But then H is 3, so although I get up here the value 14, I get the value down here is only 8, and there's this line of symmetry again. Quick check that you're moving away from that point as the source node. So I think it's 6 next to 87. So I'm looking for 87, and next to the 87, I'm hoping for 6. It is 6. Yes. Calculating class numbers in increasing difficulty. I'm enjoying this. Right, good. RFL. We wanted a thing and we got the thing. That's called reflexivity, or RFL. Right, good. The problem with that emote is that I feel I have to explain it every time I see it, which maybe ruins the punchiness. With predictions of what will happen next, we're still in emote only because I'm doing another one. 92 is even, so I feel like that might just be different in that I have to list even squares. So maybe this is a kind of, we've been ramping difficulty and now it's time for just something that's a bit different, because it's time for some even squares. But we'll keep our eyes out for whatever's going to happen in this case. So you put your 92 in here. Right, here we go again. I've got to do 92 divided by 3. That's 30 and 2/3. I'm getting better at dividing numbers by 3. He says, have I spoken too soon? No, I think I'm good. 30 and 2/3. But this time I'm looking for even numbers, even squares, because I want a multiple of 4. Luckily, that is a multiple of 4. If it was 2 mod 4, I would say there are none, because no way you can add a square to that and get a multiple of 4. Squares don't come in 2 mod 4 flavour. So we've got 30 and 2/3. Right, what are we doing? Focus in. We want even squares. So I'm going to think about 0. I think that is allowed. It's going to give me symmetry and stuff, but that's fine, I suppose. So 0, 2, 4. Do I want 6? No, 6 would be too large. So then I need to think about those 3 cases. So I suppose that is new that we've got 3 cases for H. And in the first case, AC is 92 divided by 3. 92 divided by 4 is 1 less than whatever I previously said, so 23. In this case, H is 2, so I get 4 more than 92 is 96, divided by 4 is 24. And in this case, I get 16 and 92 is 108, divided by 4 is 27. Okay, so I think there's going to be some interesting symmetry stuff here, and not here, and not there, where H and A could be equal. That's the case that I'm looking out for. I think this might go wrong at some point if 23 is prime. I think this might go wrong at some point if there's a different sort of symmetry. Yeah, so this one, for example, is happening literally as I said it, where A and C, but then H is 0. So you get 24 here and also here. So there's just one class there. Even, reflecting it doesn't give you a different picture. We're trying to look at these reduced forms, but then think a little bit about how they transform. And for proper equivalence classes, reflections count as different classes, unless it's literally the same things, in which case, same class. But this one I'm about to write down, no, it has to be larger. So 2 and 12, 3 and 8, 4 and 6. But this first one only gives me 1 because I get a symmetry down here. That there is a reflection across this line. I'm drawing a little bit of this binary tree. The binary tree is, I suppose, infinitely large, so bear with me. 12, 14, 16. So there's kind of a reflection in the line. Let's draw a bit more binary tree. There's a reflection in this line here, which means that actually any reflection gives you something that's equivalent by non-reflection stuff to the one where you do that reflection. God, that was badly explained. I'll try again. So if you do a reflection in any of the lines, you might think you have a different binary form. I mean, it has 2 on the left and 12 on the right, so you might think, aha, different numbers. But you can, in that example, you can rotate it round. So you get the 12 and the 2 switch places, but there's still a 12 below, and if you rotate it round, the 2 is now on the left again. And you can always do something like that. That whatever reflection you do, you can always transform and rotate it back to get that 12-12 edge back to where it is now, and then the reflection doesn't matter. which side is which, because there's 12 on both sides. This symmetry continues, by the way. So we have 12 here, 14 as the sum. So over this side, it's kind of binary tree branching outwards for the values that it takes on all of the pairs of numbers, coprime pairs of numbers. Has this lovely symmetry to it. It's the main thing that we study in this textbook. It's great. Right, okay. So 1 there, 2 there, and 2 there, I think. And I'm saying just 1 there because the symmetry, different sort of symmetry. That's the new thing here, I suppose. Different sort of symmetry. Possibly that is the only trap. Can I have numbers? It's not a multiple of 4. 5 is too large, so I think nope, over here. So I think total then, just 1, 2, 3, 4, 5, 6. So next to 92, I'm looking for the number 6. Next to 92. Oh, I don't have 92 in my table. This table is only 4 numbers. Why don't I have 90? Why don't I have a 92? Am I supposed to know that incredible fact about taking out squares or something? There's some relationship between this and 23 or something. Possibly it just doubles it. Right, okay, different Google search. For discriminant 92. Is this list going to tell me? Find 92 on one of these lists. Is it in this list? No. No, no. What's this? So this is H minus D for the class number. And they've got 92 in... Is it 92? 92. I can't see 92 in any of these lists. What's going on? 92 got a class number? It's a multiple of 4. Why is 92 not in any of these lists? What's going on? Oh, is it down here somewhere? I don't think so. What's the class number for discriminant 92? I'm confused. Ugh. This is a list of D such that you get that. Such that you get that. So I was expecting to see 92 in this list. I don't know why it wouldn't be. Why is it not in any of the lists? I'm so confused. Oh, am I going mad? Oh no, I know. Turning off in my only mode. Help. Chat, am I going mad? I think the number 92 is not on screen anywhere. But most other multiples of 4 are. What? I must just be wrong then. But it seems like I'm wrong whatever answer I pick. I did a search for 92 comma and I found 292. Is it actually huge? No, these are in order and these first numbers are huge. I'm going to look down here as a sort of joke, but surely not. Okay, so maybe this is a list of fundamental discriminants or something. No, what is this? Oh, I am now stuck. It was fun and games. And here we are. Right, so this table is for fundamental discriminants. Right, as far as I know. Ooh, okay. Right, although this thing has a number, this is not a fundamental discriminant. Okay, so this table doesn't have 92 in it, and the other table didn't have 92 in it. Right, because it's not a fundamental discriminant, because, let's think, it's, wait, what? Is it not a fundamental discriminant? I'm so confused. I'd have said it was fundamental discriminant because it's 4 times, ooh, hang on, it's 4 times minus 23. Minus 23 is 1 mod 4, which means that minus 23 is a There are solutions of minus 23. We had some over here, didn't we? We've already done the case minus 23. And then 4 times that is minus 92. So this is not fundamental discriminant. It's not going to turn up on those lists. I'd still like to know if I'm right. The AI overview says that the answer is 4, but it's the Google AI overview, so who knows what the answer might be. I need a better list. Oh, I need a better list. What's this? Is this what I want? I need to know that fact. Are there answers in this book? I need answers. Okay, I'm gonna say it's probably 6. Hello, Machine Rex. Welcome to the stream. We are learning about class numbers, which is quite exciting. Because when you Google them, you get all complicated maths. So it feels like you're learning about. It feels like we're learning about something important. I think I've now closed my guide. Oh no. Is this page going to be more helpful if I scroll further through this page? Ugh. Ugh. Four times a square free number. Then, yeah, hang on. Has this got 92 in one of these lists? No, it stops at 4. Okay, this page was almost helpful for this case, minus 92. I guess we're going to have to learn the relationship between different things, or hope that this book has got like solutions or something. 2 seconds, just need the link. Oh, is that a new Desmos? Interesting. So we are here in section 5.3, which is respectable, I would say. In terms of page count, we're not quite there, but respectable. I'm going to scroll through here because this one is much easier to scroll to the back. Are there solutions to slices or something? Bibliography, non-standard terminology. Ooh, some periodic separator lines. Ooh, a table of forms of positive non-square discriminants. Fully symmetric negative discriminants. Ooh, well, I don't know what this means. This table is not going to tell me about 92. Pointedly not going to tell me about 92. What's this? 92 star something x23, and then it's got some examples sort of forms. Oh, it's only got 2 examples. Oh no, kind of 3 examples of forms with a plus and minus 2. What's this then? H delta. Oh, okay. So this says 3. Oh, irritating. Okay. Why is there a star on it? Ah, right, okay. This table lists the proper equivalent classes of primitive forms for each negative discriminant up down to minus 120. So I think what we're going to find out is that I'm wrong and there's a good reason why it's not in the other tables. The first column gives the discriminant up to sign with an asterisk when it is not a fundamental discriminant. Okay, so 92 is not in the table because it's not a fundamental discriminant, not in other tables. The second column gives the class number. In most cases in the table, the class group is cyclic. Ooh, groups. Ooh. Okay, right. Factorization of the class group, fun. Okay. That's 2 times 2 means class number 4 with the class group, the product of 2 cyclic groups of order 2. The third column gives the various characters for each discriminant. Right, okay, so some of mine don't exist. I'm ignoring your Desmos link as instructed. So why do some of mine not exist? I thought I was onto a good thing here with looking at the cases. And then I thought I found all of these, like loads, where b squared minus 4ac, well, I should probably check that this does work, right? So 4 minus 4 times 2 times 12. It's quite a lot of maths to do in my head, but let's go for it. 2 times 2 times 12 is only 48. 4 times 2 times 12 is 108. 96, sorry. 4 take away 96. I think that's what I should count. Why is this not one not there? Oh, this one's not there because it's not primitive. I'm only supposed to be counting primitive quadratic forms. So trap there's a common factor in these ones, 246 and 2212. So they don't count, because for the class number we only count. It's the first thing I looked at today when I switched the stream on, was the sentence, the class number is the number of proper equivalence classes of primitive forms. And the thing that I'm learning today is that they mean that when they say it. So recapping difficulty, we saw this case where it was fine, there was only one value of h, and it did permit the solution 1123 or something with some, it was easy. This one was this the stage where we had a couple of values for h, but it didn't work, and then this one there were a couple of values for h and they gave us some solutions. This one there were a couple of values of h and they both split for symmetry reasons. This one we've got even, so we've got a different sort of symmetry, and we've got to remember that we're only looking for primitive forms. So, harder case there, only looking for primitive forms. So the correct answer was not 6, correct answer was 1 plus 2 is 3. Welcome to Chill Maths. Right, you see, escalating problems, getting harder and harder. That one also hard because it's not fundamental. So it wasn't in all the tables that I tried to cheat with. Right, we're doing another one. How many of these are there? 2 more. 2 more feels good. Oh, right, these are positive numbers. How do I feel about positive numbers? Nervous. Do my facts still work for positive numbers? Do my facts still work for positive numbers? That one still works, doesn't it? Oh no, I don't know what to do for that one. I don't know about positive discriminant at all. I'm in trouble. Yeah, help. Help, because I would expect the maths that was up here that's gone, I'd expect that to still hold. Yes, feels bad. Bad feeling about this. The maths that was up there, I would expect to still hold. Possibly you can't put those ones in the same sort of reduced form with positive numbers. That's it, isn't it? You can't put the ones... What are they called? What are they called? Come on, what are they called? They're called hyperbolic. They're called hyperbolic forms, and you can't put them in that form, but there is a related one that I should now go and learn. So, different sorts of fun and games. I'd like to scroll back a few pages, probably quite a few, to think about reduced form for hyperbolic quadratic forms, conditions on H and A and C, and that'll give me some way to solve for these things. I think it's all different, so we're going to have a look at that. Back. Here are some cases. Do I like these ones? So those look like elliptic ones to me. Is that what I want? No. Yep, okay. So yeah, back in here. We're looking at hyperbolic forms. Where are we now? I think this is looking good. So we've got that separator line. Down here? No, I wasn't wondering what would happen if I did it with different values. I've confused myself now. Yes, I've declared myself confused. We're looking at these ones, which I don't love. I would like to think about these ones. Yes, discriminant 60. Yes, here are some. Okay. Down here then? Where are we looking? It switches. Yeah, okay. Cycles of hyperbolic forms. Here we go. The topograph of a hyperbolic form. Good, right, okay. Yep, the discriminant is h squared minus 4p minus q or something, where the coefficients are p minus q and h in the middle, I think. Since p, q are positive, because the numbers on the thing are positive and negative, only finitely many possibilities. So this is the maths for checking the cases in these ones. What are we going to write these out? We're thinking about x squared plus, so we're thinking about px squared plus hxy minus qy squared as a kind of, what does that look like? And I haven't thought about reduced forms yet. But, it's going to help us out a bit, isn't it? That this thing is finite, and this thing is positive. So for PQ, a positive number is clearly, it's clearly less than 60, and at most 60 minus h squared. So at most 0 because it's a positive number. So that's a much simpler bound on things. Okay, right, new Desmos. Oh, and high resolution is a good advert. Let's have a look at that. Oh, it's the t-shirt design. It's the t-shirt design. You're trying to do the factorization for all the numbers, and you've got a kind of nice gradient here. So I've seen this before. So this is, oh look, mouse over, nice. So thank you. So 2, 3, 4. 4 splits into 4 factors in this. It's 1 plus I to the power of 4 up to factors of 1s and i's. Oh, it's very nice. 6, 7. So 6 is 2 times 3, but 2 also factorizes. 7 is prime, even in the Gaussian integers. 8. So why has 8 only got 4 things here? What was I expecting? I was expecting 8 to look different from 4. Yeah, I'm expecting an extra factor of 2, so I'm expecting 2 more. So I think I was expecting 6 sections over here for 8. And then 9 is 3 squared. And then 10 is 2 green bits, times 5, but 5 factorizes as well. 2 plus I into this blue and yellow colour. Nice little Ukraine flag. Give us 10. And then you got these nice patterns. So up here there's a 10 times 1 plus I. Yeah, just 8 where I feel like I need more lines. There's something going on here as well. 4 plus 4i. Might just be... I can't check other cubes, can I? Okay. Gaussian integers. V1. I'm impressed you've made that in Desmos. I've got some terrible Python code for that. Right, okay, so I think I could have worked this out actually. The positive cases are not too bad. I should have thought about it. I had to remember the kind of canonical form like this. I'm going to think about values of h as I go, I suppose. But it looks like h squared is at most delta. Okay, not too bad. Let's have a go at working this out. Oh my goodness, right, we're over here somewhere, aren't we? It's just question 1. Right, we're having so much fun. So over here, maybe this side for this one. We've got, so we want all the possibilities, more or less, for px squared plus hxy minus qy squared with h squared plus pq equal to, in this case, 145 for pq, discriminant. That's what we want, and those things should be integers. So there are some cases here then. This is a multiple of 4. H has got to be odd in order to give us this 145. So I'm looking for odd squares that are at most 145. Can we think of any? Yes, we can. H could be 1, 3, 5, 7. I think 9 is on the table, and maybe even 11, but not 13. 13 is too large. 4pq is going to be positive, so hpq all positive. I'm not sure I have any restrictions on the relative sizes of h and p and q, but I think about it. So let's go for some of these then. So these values are now going to bring down this value for 4pq. So I need to subtract and divide. So in the first case, I have pq is 36. In the second case, these are matched up cases. Terrible way of writing it, I'm sorry. Take off the 9, you get 136. Divide by 4, you get 25 plus another 9 is 34, I think. If you take off 25, then you get 120, divide by 4 is 30. If you take off 49, you get 96, divide by 4 is 24. If you take off 81, you get 64, divide by 4 is 16. And if you take off 121, you get 24, divide by 4 is 6. I think I probably got half of those right. So good start. There are loads of these then. This is going to be crazy. What's this factorization up here? How does this factorize? A bit suspicious. Right, so it's 5 times 29. Oh, okay, fine. Carry on, everyone. This is going to be a fixed version of this, isn't it? Let's have a look. Yeah, he fixed it. 6 down here, that's what I wanted. Because 8 is a bit like 1 plus I to the power of 6. Kind of nice. Oh, does anyone else get weird effects if you look between the dots, between the circles? Yeah, very nice. So you have these multiples of 3. The multiples of 3 you can see lie on this kind of grid, square grid, where the bits of red, you see red here and here and here and here and here and here and here, in this kind of square grid. Going up from 3 and 6 and 9. But also the complex part has to be a multiple of 3. So you have multiple of 3 here and here and here. And then like that, you get these kind of square grids. But then the rule is whenever you have a full square like this, that defines a square grid from the origin down in this corner, not shown. So this lime colour appears in a square grid that's a bit hard to follow, but going out this way, here, and here, and here just a little bit, and here twice. Like following that way, and also walking the other way. So walking this way, 1, 2, 3. And so there's some yellowy lime stuff going out in that direction as well. Yeah, so it doesn't also, I guess you're right, lets you zoom in lots. So you can get extraordinarily high quality if you're willing to piece together screenshots. Yeah. So that works. Nice, thanks. Okay, right. I was in the mode though, wasn't I, where I was doing this calculation. Let's think about PQ as 6, H as 11 first. So I think that factorises lots of different ways. So do I have to think about 1, 6 and 2, 3 separately for P and Q? Well, let's check them. So then I'd get 1 minus 6 for some values. This one feels a lot harder than the other ones. H is 11, and H is still the change when I go over this. So from minus 5, I'd go up by 11 to 6, and I'd go down to, what is that? Minus 5, take off 6 is minus 11, I think. So for example, when you put in 1, 1, you get P minus Q, 1 minus 6, plus H. H is 11 in this case. So 1 minus 6 is minus 5, plus 11 is 6. Let's check that with the quadratic form checking thing. The quadratic form in this case is 1, and then H is 11, and then this coefficient is minus 6. So I get 1 minus 6. Oh, I've messed up that number down there, have I? So H is 11, so I was at minus 5, I should go to minus 16. Okay. Fair dues. Minus 16. So I can't see any symmetry here. What about this 2, 3 case? So H is 11, so 5 I go up to 16, and I come down from 5 to minus 6, which is a different case. If I put in P is 2, and this is minus 3, but keep H as 11, I've subtracted wrong again, because it's minus 3. So this is minus 3. I should remember there are positive and negative numbers going around. Be careful. So minus 1 plus 11 is 10. Minus 1 take off 11 is minus 12. Okay, values everywhere. I think these have got, you reflect it, you get a different one. So I think we're finding 2. The class splits under reflection in each of these cases. This is going to be tough to look up, isn't it? I'm not certain if 145 is going to be in the big table. I'm going to press on because I've got about 5 minutes of stream, so I think I should try and finish this calculation. So 16 is going to give me something like all the ways to factorise 16, yeah, minus signs count, I think. So there's some translation stuff going on, maybe. I should be a bit careful. Because I think I'm going to find this minus 16 case now. Right? I'm going to find this minus 16 case. I need to walk along the periodic separator line, working out how many of these are in the same cycle as each other. Right. Fun. Okay. And this is going to be part of the 36 case, look. So I need to explore all of these as I build them until I find out the periodic behavior. So that's hard. So -6 minus 15 is an increase of 9, and then the next number is going to be, okay, so instead of doing the calculation, I think I'm going to look at the pictures. I'm going to speed this up. Instead of doing all of the arithmetic adding, I'm going to say we're exploring, and I'm going to use this tool to explore. That's a bit cheeky, but we're going to go for it. So with an 11 in the middle, we can see that following the separator line, has this got separator line properties? It does. Good. Thank you for coding that. It's mostly Maths 22222 stream, really. I'm just here clicking on stuff. Separator line looks like this, and then we can follow it. So I wanted to follow it over here, and I get the value of -24, and then -30. Does this keep going? -36. What happens after the -36? So the separator line should be periodic, right? So I should maybe go a bit deeper. That just makes that deeper. So then it comes back again. Oh my goodness, it goes back through. And then it'll go back through these numbers. So now it's coming back up again. -34, 30, -24, -16, -6. So it'll come back up through those values. And then, oh, there's so much separator line, right? Okay, and over here, there's something periodic going on. So after it's done that bit, -1. Over here, it's got a kind of bit going on with minus the negative of that number around here. Oh, this is not a 5-minute calculation, is it? So in this one, if you keep exploring, you find pairs like across the separator line. It's not enough for me to just note down what you find, is it? I have to write down the value of h as well. Oh, is this a 5-minute job? Hey, if you've just joined us. This is Chill Maths on Twitch, where I'm trying to find the class number for the value of the discriminant 145, which is a positive number, so I've got to think about these periodic separator lines in the top graph of the fairy diagram. It's a whole thing. It's not extremely chill. And this one seems like a really hard case because it's just going to keep going and going and going. Instead of drawing them like this, I should be drawing them it's going to bounce around loads, which I suppose means, yeah, so for each of these I should count, has it explored some of these other ones? So there are these other starting points. Yeah, I've got loads of solutions for like things that multiply to give 36. I've got loads of those, and the PQ things are positive and negative values that you can switch around the pairs, except for the 6, 6 one, because 36 is square. Oh my goodness. 36 has got 9 factors, so that's 9 factors. So yeah, I should write down these 9 things. There's no switchy doesn't count on that. It doesn't save you at all. So I think I need a table which has values of h and then values of p and q over here. I've seen this somewhere. 1, 3, 5, 7, 9, 11, and then pq. So we go for when h is 1, we're going to list all the ways to make 36. There are 9 of them. 6, 6 is next. That's as wide as the page will go. Extend this line down a lot. 6, 6, 9, 4, 12, 3, 18, 2, 36, 1. And then the next case is 3, where we've got to make 34. Well, 34 is not prime, so count your blessings. 34, 1. And then in 5, 30. Oh my goodness. 30 is 2 times 3 times 5. So it's got 8 factors. And then for each of these, you could start drawing the periodic separator line. And the question is, how far do you have to go before you get back to where you were? And which things have you gone through on the way? Can I list the factors of 30 while talking? Let's find out. 7 gives you a value of 24. 24 is 2 cubes times 3, so it's got 8 factors. So there's so many like starting points to explore from, and you'll cover lots of them along the way, but this feels excessive as a sort of task. It's kind of amazing that, well, not quite amazing that anyone could do this, but he's currently doing it. But you know, finding the class number seems quite hard for these ones, where you must walk along the periodic separator line. Look at this. So when h is 9, that's where we're in the case 16, so I need to list lots of powers of 2. 4, 4, 8, 2, 16, 1. And then when h is 11, we're in the 6th case. 1, 6, 2, 3, 3, 2, 6, 1. So 4, 5, 6, 7, 8, 9. And then 16 of these is 25. 29, and then 7 is a total of 36, I think, states that we can be in. And some of them are linked together. They're secretly the same quadratic form, different points along the periodic separator line. And the question is, how many different separator lines do you actually get? How many of these are just at the same point along different lines? Feels like 2 or 3. We can start exploring one of them. So let's try and do that using our... It's a bit cheaty, but let's try and use our calculator to say, just for this one, we've got this separator line here, which is going to pair up. So, for example, 1 minus 6, I can see on the plan. Tells me, oh, okay, so I can just look at the values of PQ, because that will give me the value of PQ, and then delta is fixed, so h squared minus PQ for PQ is all good. We're going to be fine. Let's turn down the label depth a little bit. There we go. Oh, maybe I need that back just for the sequencing. Right, okay. So we start at 1, 6. This is good because I can point at this and write underneath. I'm going to run a little bit long. We're going to find out. So 1, 6 down here. Let's change colour. Let's see. Let's hope there's not too many of them. So in blue, I'm going to underline things that we see. And we've started over here. This is a case where h is 11 to start off with. Which in the canonical form over here is the middle coefficient on that quadratic form. So we've got a case 1 minus 6, so I underline that one because we've seen it. And then I've got case 6 minus 6, so I underline this because we've now seen that. And then the periodic separator line goes over here to 6, 1. I need to be careful to read the positive number first. 6, 1 is down here again, over here. And then it goes 16, 1, which is here. And then 24, 1. I'm trying to read positive first, but actually say, because there's a minus q in there somewhere. So 30, 34. So 30 is here. 34, 1 is there. I need a little bit more label depth now. 36, because then after the 36, it's going to come back again. The periodic separator line has this symmetry to it. So after 36, it's going to come back. And it's going to work its way down through those values. So let's look in the other direction, where we'd said we had 1, 6. Let's go the other way, because I can also see 1, 16, which is here. So all the way back through to where we started, which is down here. 1, 6. To the left of that's 1 minus 16, 1 minus 24, and I can see 1 minus 30, 1 minus 34 is next, and then it comes back again. So in blue, those are the ones that belong to just one just one equivalence class of quadratic forms. Right, let's do another one. So we've got several things not covered by these cases. Let's put 2 and 3 in here. So this is genuinely a different quadratic form, one that we haven't seen yet. Turn down that label depth to start off with. It's got this 2 minus 3 edge, which we haven't seen yet. For the same discriminant, that's got a different value of h. It's going to do different things. So once again, I'd like to walk to the right, I think, and I need to reset the separator line. Have I got a reset? Yeah. Oh, this tool's brilliant. Thank you, Maths222 in chat. Building this thing. Let's just visualize this so nicely. Right, let's go over here, and then over here. So you're sort of following this binary tree, looking for negative values. I think I'm going to need a bit more label depth over there, but we'll explore that way when we get there. Ready? Okay, so 2, 3. I'm going to change colour to red. I really hope there's only 2 or 3 of these. Look how many things we explored though. out of our 36 states that we could be in, we explored 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, a third of them. Interesting. Maybe there'll be 3. It'd be nice if that was a rule. Okay, so 2, 3 is a state that we've seen. I'll put that in red over there. And then walking to the right, we see 10, 3, which is in this over here. And then we see 12, 3, which is this case here. And then we see 8, 3. So remember, there's transformations that let us move edges around in this diagram. And we consider those to be equivalent forms. So by finding more edges like this that exist in this picture, we're showing that things are equivalent. 8, 2, 15, 2 is what's happening next. So I'm waiting for this to turn around or repeat or something. I'm going to need more label depth over here, I think. Yep, to find out where the separator line goes. So 18, 2. Have I already seen 18, 2? No. And then what's this? 17, 2. And now surely it's got to come back again. It's a kind of quadratic shape, right? It's going to come back down, I think. Label depth, please be 18 just there. 12. 12, 2. Is 12, 2 new? 12, 2 is new. Oh, it's coming down? No, I don't know what it's doing. Okay. More. 3, 2. More. Oh my goodness. So then it turns this way. So separator line comes through here. Then it turns this way to give us 3, 10. Oh, okay, bored of this. 3, 10, which we haven't seen yet. And then what? So I could work this out by hand if I have to. 3 minus 12. So underline 3, 12, which is up here. It's still doing new stuff. I've hit my label depth. Let me go to 11 just to see what happens. I might crash my computer. I'm hoping it will repeat. Yeah, I guess it's doing about twice as much work each time I up that. So we're in danger of crashing everything. Yeah, okay, we might switch to manual mode. Switch to manual. Turn this back down to 10 so it stops thinking. Switch to manual mode. So we found this bit 3. We've got this bit of space, minus 10. And then the value on the left over here. There's a value minus 12 here. So I'm interested in what's going on next over here as I follow that separator line across these negative numbers. So I have minus 10, minus 9, so this will be minus 8 as the next thing that I see. You can sort of follow it, right? Let's be really careful because I just said something that might or might not be true. Yep, no, minus 10, minus 9, minus 8. So I should underline 3, 8 next. I'm amazed how far we've got through on this one. I can't see 3, 8. 3, 8's there. And then keep going. 3, 8. So minus 12, minus 5 is an increase of 7. Minus 5 on the next thing will be 2. Oh my goodness. So I want to go that way. So I've seen 2 minus 8 as this edge, which is that one. Oh my goodness, I now think we're going to see everything. We're still exploring. We haven't got back to the things we've seen before. 3 minus 6 is a decrease of 9, so decrease by 9 again. So from minus 6, we'll get down to minus 15. So now I'm looking at 215. This is going to do everything now, isn't it? This is just going to do everything. Separation line goes this way, over there, so I'm just trying to explore around what's going on over this bit. Oh my goodness. So 2 minus 15, so minus 8 minus 13 is a decrease of 5. Minus 8 minus 13 is a decrease of 5. So minus 18 is next. So I should underline 2, 18, which is over here somewhere. Followed by, at that point we go over here, we have minus 15, minus 16, so minus 17. So I underline 2, 17. Almost there, I think, maybe. Over there we have minus 18, minus 15 is an increase of 3, so minus 12. So I underline 2, 12. steam coming off my head. 212 is one of the only things I haven't underlined yet. And then from there we have minus 17. Oh, I've written really small. Minus 17 minus 10 is an increase of 7, so minus 3 is next. And we get to 2, 3, which I think is where we started. So following it all the way around, we get all of that. Fun. That was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 things in the cycle for that one. Quite a lot. We're going to turn this down because I'm rendering way too much stuff. We're going to reset the colors. We're going to zoom back out. And the next one can't be that long. We're going to start with 4, 4, I think, for the values 4 and minus 4. Oh, and what can we see? So we've got a separated line that does this, and it does 11, 4 as well. I need a third colour. Have I got any more colours? I have grey. We'll deal with grey. So 4, 4. And it feels like this might be the last one if it does anything interesting. So, oh, I don't know about 11 minus 4. I don't recognise that case at all. What have I done? I'm not supposed to start with an 11 in the middle. I'm supposed to start with a 9 in the middle because I've switched to looking at one that starts when h is 9. So a separated line does this. It goes over there. Oh, it's coming back again. It's coming back again. There's a line of symmetry. Oh, I should have been keeping track of if there was a line of symmetry or not. That's really annoying. The blue one, I think they all do. Whatever. I'm going to say they all do. Oh, that's quite annoying. Did it have a line of symmetry? I think they all do. I'm counting these once each. The answer is going to be 3, I reckon. If not, then I'm very sad. Right, 9, 4. I can see 6, 4, which is over here, amazingly. And then I can see 6, 5, which is over 6, 5. 6, 5's over here. And then it's repeating. But reading the other way, I get kind of minus signs. So I get 4, 9, reading the other way instead of 9, 4. So yeah, I like this with the 4x squared and the minus 4y squared. It's kind of, what do you do? If you switch x and y, you get, not quite that. If you put minus signs on both x and y, you get, do you get negative the number you thought you would? And switch x and y. Some of that. Some of that. Possibly a minus sign on one of them. Yes, if you switch x and y, if you switch the values of x and y, then the middle term doesn't care. But the outer terms, that's like multiplied by minus 1 because you have 4x squared. Now you have minus 4x squared. So if you also multiply one of x or y by minus 1. Yeah. Good point. We haven't seen 136. That's a very good point. I might have missed it on one of my rounds. We'll try that one last. Okay, so reading left, I'm going to get 4, 9. And then, I think I'm just missing that 1 point, which I might have forgotten to mark. But yeah, okay, suspicious. That's going to stop the answer from being 3, isn't it? 4, 6 I can see. And then 4, 5. 4, 6. Oh no, not 4, 5. 5, 6. 4, 5's not on my board. Yeah, and then it's going to come back again, line of symmetry, and do all of those. So it only left me with the case 136, which, I don't know, could it be on its own? That would be weird. What's h in that case? H is just 1. Which is not on its own, it's paired with one of the 34s and stuff. That's irritating. I thought I had this case already. Bother. Interesting. Also, this case doesn't look like... What's this? So it's got loads of the things I thought I'd seen in my blue case. Let's put the blue case back on the board. I think this has got, reset the colours. This has got an edge with 1 minus 30. I'm confused now. This has got an edge with 130. Ah, I did just miss 136. It was in here. It was blue. I did just miss it. Right, and missing it is the same as... Okay, so said differently, if I go back to the new interesting one that I thought I'd missed, with 36 in it, and if I look in the corner, so I have to look quite far away, but quite far away I'm panicking, but if I look over here, I see 1 minus 6, and I think, ah, great, that's an edge. A little bit more depth on the picture. That's lovely. I see a 1 minus 6 down here. That edge there is the edge that I kind of started with in my blue case. Phew, so I just missed one of them. Missed any more? No. I think the answer is 3 after all of that. And we're going to look at the big table, and this was 145? 145? Something like that. Question has completely disappeared. Oh, it's up here. 145. I think the answer is 3. If not, then there's some fact that one of them didn't have mirror symmetry. I'm open to the idea it might be 4. 145 is not on this table. What's the problem with 145? 145 is... No, hang on. So 145 feels like it's a fundamental one, right? Is 145 not fundamental? Okay, well, I'm going to look it up in the TN book table. The TN table only goes to 120. Hooray! Are there answers in the back of this book? Can I just look at the answers? No. There are no answers in the back of this book. Oh no. The table has betrayed us. Oh dear. I don't have the energy to check this another way, do I? Why is 145 not in the table? It feels fundamental to me. Oh, but that one was only... So what? Okay, interesting question. Why is 145 not on the table? If I factorised it wrong, is it not actually 5 times 29? It's definitely 5 times 29. Now in grey. Blue. Now in blue. I click on that Wolfram page. It's not going to be on this page, is it? Because I think it's, for reasons I don't understand, it's not fundamental or something. So it's not in this list, but it's not in any of these lists because it's not fundamental. Oh, what's this? Ah, so there's 4. I was open to the idea of it being 4. Why is it 4 then? So is the really long sequence not symmetric? That's so weird. Okay, I don't know what's going on there. It's the smallest one with class number 4, I'm told, in the list below. Why is it 4? I'm not going to ask ChatGPT. So one of these, oh, is one of these not primitive or something? No, hang on. Think hard. Is one of these not primitive? Is one of these, is it the red one? No. Blue one? No. So there's some interesting values in all of these. Is the red one everything even? No. And the grey one is everything even? Or no, because there's 4s and 9s in there. And values like 4s and 9s. There's no common factors there. In the grey one, I think they're all primitive. So it'll be a symmetry of one of these. Possibly the very long red one. But I thought the periodic separator line always had a mirror symmetry thing going on. Maybe that's just for continued fractions. Okay, so I think what I want to do is, to check that, is to look at the Desmos again. Oh, I've got a lot of tabs open now. Let's leave that one. I've got maybe too many tabs. Let's consolidate some of them into one large tab. That can come in here, that can come in here. Last thing I think for today is going to be just to have a quick look at my candidates for 3, which I think we found all of them. I don't think this splits anymore. The fact that we can keep exploring until we found all of these. So my candidates are canonical forms like this, with a clear line of symmetry. So that one's definitely just 1. And I think, what else do I have in blue? So then the grey one, I want to think about 4. So 1, so 4 and 9. This one I think doesn't have a line of symmetry. Oh, so this one splits, right? No. Oh no, maybe it does. Let's have a look in. So find the points where it does this. So is there a line of symmetry somewhere way over here? Yes, over here, look. 5 and then -6, -6. So there's a line of symmetry on this one as well. This is the grey one with 4 and -9. So then possibly this red one that I had to go and draw on the board a little bit as well doesn't have a line of symmetry. And you get a different form if you reflect it. Am I overthinking this? I don't think I'm overthinking this. Possibly this doesn't have a line of symmetry. As we were exploring, we hit the start point. We didn't start looping back through things we'd already seen. So the way it happened, right? We were exhausted. We explored all this way and it didn't come back. So I think a healthy thing to do would be to draw the periodic separator line, which doesn't have a reflection image, because that will really force me to learn that. Yeah, okay, I like that as well. Yeah, we can do the transforms to it to visualize what's going on. So let's turn down the label depth and just look at it like that. And yeah, okay. So I'm going to try and draw the periodic separator line, which is going to be long. I'm going to draw it. We think it's going to go through about 18 states, but I'm going to try and draw it out with the periodic separator line horizontal under here. And this is going to be red case, is what it's called. Red case. Really long separator line. And I'm going to keep track of positive numbers above and negative numbers below. And I am starting, for want of a better choice, at the point where it is 2 and -18. And the next thing I can see, so here we go. The next thing I can see is 2 and -15. So exploring off this way, I can see a 2 and a -8. And these branches, so I'm trying to draw this, I'm bending it round. So the 2 is at the top, and -18, -15, -8. But then the next thing I see, if I'm following the separator line between positive and negative numbers, is 3 up here. So the next thing I see is 3 with -8. And then 3 sees -12. And then it's going a little bit too far to the left. So I'm going to pause that activity for a second and read off stuff I can see on this side instead, where there's a -17 and a -12 and a -3. And what's this down here? And over here we see -3 and 10. So I think I'm interested in putting something like 312 in the middle, which I can do like this. So there's another point on the red curve, so 312 like this. And on the left I can see that, no wait, why is it on the right now? Now it's on the right. That's annoying. Why has it done that? Transform? No, don't do that. Yeah, do that. Was it 10 or -10? Good question. Not sure. I'm going to erase it just in case. There's confusion, so we're going to not comment on which way around it is. Blob. But now we've got a 3 -12 with -8 on the left. So this bit, and I can read off a bit more. Good idea. We can just keep reading. 3 -10, 3 -2. This is still new stuff, isn't it? 3, and then 12 minus 2. And then 17 minus 2 and 18 minus 2. And then I'm a bit confused, but I'm now at an 18-2 junction. So I'm going to go 18-2. And which way do I want to go? I can't see any negative numbers now. Let's, what can I not see? I can't see. Oh, right. Okay. Reset the lines. So 17 coming around this side. I've got 17, then 18, and the next thing is 15 next to a minus 2, and then 8 next to a minus 2, and then finally 8 next to a minus 3, which is exciting to me. So 15. Where am I? So I've got my 18 next to a minus 2, and then 15. So I need a bit more line here. 15, and then 8 next to a minus 2, and then 8 next to a minus 3. And after that is 12 next to a minus 3. And then I'm a bit lost again. But now I can reset it to 12 minus 3. And hopefully this is going to loop around. Reset. I've got a minus 3 underneath, which is good. So I've got this 12 minus 3. I'm going to flip it in the middle just like that to switch around above and below so that I keep my... It doesn't really matter, but I'm keeping the parity the same way around as the picture I'm drawing at the bottom. 10 minus 3 followed by 2 minus 3, at which point it repeats. So this was a 10 over here. And then to the left of the 10 is 12. And then to the left of the 12 is 8. So this bit is drawn on the picture twice. 8 and 12 over here, 8 and 12. So it goes through those things. I'm going to tidy up the picture a little bit by moving the labels to the middle of their zones. I don't quite know how to move these ones to the middle of their zones. They're infinitely large. But it does this pattern, which, right, and this has been important for me because maybe you can see, there you go, maybe you can see the sort of symmetry that this does have, which is not a reflection symmetry like this, as you read along, but there is some pattern to it. It's not just random numbers. It is quite long, isn't it? So it goes 8, 12, 10 along the top, 2 along the top, and minus 3, minus 12, 17, 18, 15, 8, and then it switches to a 3. And it goes along with around 3, it goes 8, minus 8, 12, 10, 2, and then 12, 17, 18, 15, 8, 12, which maybe you notice is related to this sequence of numbers. That there is a sort of glide symmetry here, where you can take the sequence of numbers. Have I got 17 of them? Oh, right, okay, let's have a check. So pairs, not counting the 8 minus 3 the second time, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yeah, 17 of them, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Bother, I've missed something. But maybe I can use my pattern spotting to work out what it was. Maybe 8, 2, 3, and then 2, 3 on the 8s, and then 12 after the 8. 10, oh, hasn't worked. 12, 10, 8, 12, 10, 2. 17 things this time. That's annoying. I think I have 18 on my picture on the right. That's very annoying. What am I going to do? Did I count 8 minus 2? Not sure. Not sure I did. So let's count. Let's count together. We can say that we're highlighting the separator line as what we're doing. So this is the boundary between 8 and minus 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I didn't count the 8 minus 2. Thank you, Lewis, Hamiltonian Dynamics in chat. I didn't count the 8 minus 2. There we go. Phew. 18 things in the 18 distinct edges in the periodic separator line. So class number is 4, because this one has a mirror image. If I switch, and I've been doing it lots, right, which is cheeky, but I've been doing it a lot to switch like this, which does a mirror image, but these are actually different. They have the same. So I've been sort of, when I change these numbers, if I'm not careful, then I'll change to something that is genuinely a different, it's not a properly equivalent. It might be a reflection of the one. If just by typing in the numbers that I would like to see on the left and right, well, I'm biased there between whether I'm seeing 3 minus 2 or minus 3, 2. Sort of some plus or minus sign stuff going on. Is that what I mean? Whether on the left or right? Yeah. So these transformations they can rotate. Left and right could be rotated around. I can't reflect along the line. Yeah, so it's whether after 3, 2, what's coming next, which is complicated. Okay, right, good. We're going to call it there, I think. It's 6:30. Probably time for dinner or something. Thanks for joining in with the 4 o'clock stream. It is already 6:30. Yeah, this last one, I thought it would take me 5 minutes. It took me 35 minutes. That's maths. Mary always wants another 10 minutes for more channel points. We're going to leave as an exercise the calculation with, where is it? Last one. We haven't done 148, which is a multiple of 4. It's 4 times. I was getting so good at dividing, I really thought I could do that. 4 times 25 and 12 is 37. So it's of the form 37 is a number that's 1 mod 4. So there is some a quadratic form with discriminant 37, which means that it's not fundamental and it won't show up. 147. I can do this with no spoilers. 148 is not on this list. It's mostly only got odd numbers anyway. And 148, it's no spoilers to say 148 because it's not a fundamental discriminant. It's not on any of these lists. I think that's actually true. Imagine if I got it wrong the other way around as well. Oh yeah, I have. Okay, why is that fundamental? Right, okay, we're doing the other way around. Why is that fundamental? 148. Okay, I've got one more thing to think. 25 and 12 is 37. But 37 is 1 more 4. So it's not fundamental, right? Why is 148 fundamental? Not equal to 1. Not divisible by any square of an odd prime. True. And satisfies D as 1. 1 more 4. Or 8 or 12 mod 16. What is 140? Sorry, 148. 148 is. I'm not wrong, it's 37 times 4, right? 120 and 28, yeah. 37, so it's 4. What is it, mod 16? It is, oh, it didn't say it, okay. It's 12 mod 16. What do we say then? So it's 4 times n, where n is 1 more 4. Then it can be done, right? So I thought the fundamental ones, we had a list of them before. Which of these cases do we think it's in? We have a whole list, right? Other than minus 4 and plus minus 8 for 3 types. 148 is 4 times 37. So is it this? Is it this? Is 37 actually 3 mod 4? That'd be the funniest thing. I'm going mad. It's not 4n where n is 3 mod 4. Is there a minus sign hiding in here? So it wouldn't be unusual, would it, for there to be just a minus sign hiding in, which messes up all my mods. No, this really looks like it's telling me about discriminant delta, not minus delta. And 37's on this list. So 37's fundamental and also 4 times 37. I am going mad. I'm sure I'm going mad. I'm sure I'm going mad. 37 really is 1 more 4. It really is. 4 times 37 really is 148. It's 12 mod 16. It's not a multiple of 8. It's not a multiple of distinct odd primes. And I don't think it fits in this middle case either. Yeah, I think it's not fundamental. I think it's not fundamental, and I can't explain why it's on 148. I think it's not fundamental, and I can't explain why it's on this list. Because this is supposed to be a list of fundamental discriminants. And I think I'd like to go home now. Definitely on this list? It is on this list. Yeah. It's on this list. Wait, negated. I just want it. I think it's time to go home. I think it's time to go home. Does OEIS say... I don't know what the language here means. So in Parry, is fundamental of minus n. Is this actually a list of... This is a list of the negative ones, isn't it? This is a list of the negative ones. Minus 148. It's in the table because minus 148 is a fundamental discriminant, because minus 148 is a totally different problem. Minus 148 is 4 times minus 37, which is 3 mod 4. We're doing 148, positive number, which is nothing to do with this table. This table only says things about negative discriminants. It's got nothing to do with positive numbers. 148 is not fundamental. It wouldn't appear in that table even if that table talked about positive discriminants. That table doesn't say anything about positive discriminants. This other one does, but doesn't mention things that aren't fundamental. It's not in that list either. It's not fundamental. I don't know what its class number is. We're going to leave that as homework, but it might not be 2 because that table was telling us about minus 148. There are so many hidden minus signs around. We are doing it. Right, good, that'll do. And if that's not the quintessential experience of learning mathematics, then I don't know what is. These two books don't agree. One of these is wrong and one of these is right. Oh no, they're both right and I'm wrong. That's what learning maths is like. See you next week, everyone. Have a good evening, have a good week, and I'll be back for some more chill maths next Sunday afternoon. Bye. I'm ending the stream now.